our job now is to find a solution. And so what I've done is I've copied down here, so we don't have to keep scrolling back and forth, the key pieces from your notes that you have already in your notes from up above. We have a little diagram of our circuit. We have the governing equation, which we derived for the charge on our capacitor with this sign convention. And I also have a sketch for you here of what our AC drive looks like. Our task now is to try to determine how this system responds. And if we can find a solution, that will tell us the behavior of the circuit. So we have to find a solution to this differential equation. And the way we find the solution to a differential equation, bottom line, no matter how many techniques we try to teach you and to tell you about, there really is only one good technique. And it's the same technique we use to do integrals. Remember, because an integral is the solution of the simplest differential equation, namely, here's the derivative, what was the original function? And the bottom line, only way to do an integral is to take a good guess and to verify it. So we have to find a good guess for the solution to this, and then we verify to see if we guess appropriately. So, if we want to think a little bit about the physics that's going on here, we have this, cosinusoidal drive. We have this AC voltage that is driving this particular circuit, and we want to think, well, what kind of response can we expect out of it? So let's think in terms of the current, because that's one of the things that we typically measure in our circuit. We don't typically measure directly the charge on the capacitor, but if I think of the current flowing through my circuit, it's likely a very good guess that if I'm oscillating, pushing back and forth a voltage here, I'm going to get a back and forth type of response for the current. I don't know what the what the amplitude of that current response is going to be, but it's probably oscillating as well. If I'm driving it with a certain period t and a corresponding frequency omega, I would expect that if I'm pushing back and forth once every 2 seconds here, the current should probably slosh back and forth once every 2 seconds as well. So I would think then that the current has the same frequency omega t, right, as the voltage. What I don't know though is when the current is going to be hitting its maximum values or not. Right? I don't really know what phase I should put inside of this cosine. And here's where we're going to play just a little bit of a mathematical trick, because we do have one thing going for us in terms of solving for the physical behavior of this system, and that is that we do always have the choice of choosing an origin for our time, right? We can always choose at what instant we hit the button on our stopwatch that we call time t equals 0. So what we will decide to do is to call that point in time where the current reaches its maximum value of I naught. That's where we are going to start our stopwatch. And then, of course, the current will oscillate, as it will. When I do that, when I make that choice for time t equals 0, I am saying then that my current as a function has no phase shift in it. It's just cosine omega t hitting its maximum value right at time t equals 0. That's my definition of time t equals 0. Now, the way we've set up the mathematics, you'll notice, allows us to do this, because we're not biasing anything. We're not saying that the current hits its maximum at the same time that the drive hits its maximum. We're not saying that it happens after or before, because after all, phi could end up to be positive or negative. Phi will tell us, though, the relationship between the times when we hit the maximum voltage and the times we hit the maximum current. So we have all the freedom we need then to find a solution to our differential equation. So this is going to be our educated guess. And it's our job then to verify this guess. Now, to verify it, what we will do now is to insert our current into this equation and then to try to solve. To do that, though, of course, we will need to know the charge Q. We already know dq dt. That actually is the current that I've written down. And d squared q dt squared would just be the time derivative of my current. But we also need to determine the current Q. And that's determined by a fairly simple differential equation. We know that dq dt actually equals the current I, and we will go then along with our guess of I naught times cosine of omega t. This is a simple differential equation we can solve by integrating. The integral then q would be, when I integrate this with respect to time t, the integral of cosine gives me the sine function. I will have I naught sine of omega t. I'm writing that up high because I realize when I take the derivative of this charge, I will pull out an extra factor of omega that I don't want for dq in dq dt. So it should be I naught over omega. When I take the derivative, the omega comes out and cancels. The sine turns to a cosine, and I've done my integral appropriately. There's just some unknown constant shift that I have to also include. We would typically write plus capital C, but we have the capacitance in here as a variable. So I will call that plus capital D. Now, we need to determine this integration constant. What it represents, notice, is that what I'm saying here is that charge Q, if I were to make a graph of it, right, charge Q is also an oscillating function, and if I include some value of D, D will be the average value of my oscillations, right? I'd be saying the charge is oscillating somewhere around some mean value of D. And that just does seem a little bit unlikely, doesn't it? Because I'm driving this thing back and forth, right? If there were any average charge on my capacitor, you would think that that would tend to leak out eventually through the resistor. So I'm going to say we think probably that D is going to be 0. But we will be able to verify that momentarily. So I've got now my charge Q. I then would need to also to insert into my equation compute dq dt and d squared q dt squared. But I think we can certainly take these derivatives fairly straightforwardly. So let me try then now to substitute now all of this into my equation. So let me substitute into the equation. And then when I do that, for E, I have, of course, E naught cosine of omega t minus my phase shift. And that now is supposed to equal L times, I have to now take the second derivative of this function. When I take the first derivative of Q, of course, what I get when I take that first derivative is I naught cosine omega t. When I take another time derivative, I'll get an extra factor of omega will come out. Cosine's derivative gives me a minus sign and then gives me the sine function. So I'm going to have then L times minus omega I naught times then sine of omega t. The next term is the resistor term, and the resistor is multiplying dq dt, which is just my current. It's I naught cosine of omega t. And then finally, I have 1 over c times my charge. My charge is I naught over omega. When I divide that by c, I'm going to have then a term that goes like I naught over omega c times sine of omega t. And I also have this plus d term, which I'm hoping will be 0, but that also gets divided by c because our job is to write q over c. Now, we look at this and we ask, well, is there any chance that this is going to work out, that the two sides of these equations will line up? At first sight, it may not look too promising, but if we begin to think about this cosine function and we think about our trig identities, something is going to work in our favor. You might recall here, actually, that if we look at the cosine of the difference between two angles, you might recall there's a rule that the cosine of A minus B is equal to, you remember, it's the cosine of the first angle times the cosine of the second angle. You might remember the addition formula. In the addition formula, it's cosine, cosine minus sine times sine, right? So I need to write after cosine of A, I would have to write the cosine of minus b, but the cosine of minus b actually is the cosine of b. Then I have minus the product of the sine of the two angles being added, which is a. And then I need the sine of minus b. But the sine of minus b is just the sine of b with a minus sign. So I actually get a plus sign for the angle difference formula for the cosine. So let's then write these terms out. I've got my two different angles, right, A and B. So the first term, notice, is going to give me some E naught cosine omega t times cosine of phi. And that's interesting. So there's a cosine omega t term over here, and there's going to be a cosine omega t term on this side. So let me gather together the sines and the cosines on both sides of my equation. So when I substitute in for here, I will have E naught times the product of the two cosines, so times cosine phi times cosine of omega t. And the second term comes in with a plus sign because I had a difference here. And I will have epsilon naught times the sine of phi times the sine of omega t. And what this has to equal, if I gather all my terms together, I'll write the cosine term first. There's r times I naught times cosine of omega t is the first term. The sine term has two contributions, so there's going to be plus, and there's an I naught over omega c from this term minus L, let's not forget there's an L, right? There's an L omega times I naught. All that multiplies sine of omega t. And then finally I have my final term plus d over c. Now, when we compare these two sides, we see, okay, if these are going to line up, if these are going to work, what has to happen is I need a cosine part and a sine part. Here we've got a cosine part. Here we have a sine part. And we have this extra part that we don't like, right? But it looks like our initial guess was indeed correct, that d should be 0. And if we choose d to be 0 when we integrate here to determine our charge, then indeed these equations here will line up. I just need it to be the case that I have the following condition, and I need to solve, that the amplitude of the voltage times the cosine of that phase shift would need to be r times I naught. Now that is starting to sound a lot like v equals IR. So let me write it in our more familiar order. So if that lines up, then the cosine terms would be exactly equal. And then the last condition I need to find a way to satisfy is that E naught times the sine of phi will have to equal all of the things multiplying sine omega t. And once again, let's write this sort of in a standard order. Let me pull out I naught. Then I've got one term which is kind of acting like a resistance. I'll call it 1 over omega c. And then the other term multiplying I naught seems to be L times omega. And then that multiplies sine omega t, and I have a sine omega t here. So these are the conditions that I would need to satisfy in order for my guess to a solution to have been correct. Now, this is a complicated trigonometric equation to find E naught and phi. But there's a very handy graphical construction that helps us solve this equation. Because notice, if I make a nice right triangle like so, where this angle is phi, and this is a right angle, and this hypotenuse has length E naught, then E naught times cosine gives me the adjacent side would have to be I naught times the resistance. And then E naught times sine phi would give me the opposite side, which then has to have the value of I naught times 1 over omega c minus L times omega. Now, when we look at this, we can immediately solve for what E naught and phi would have to be, using our basic knowledge of right triangles. Right? We find immediately then that the voltage, the amplitude of the voltage, by the Pythagorean theorem is going to be the square root of the sum of the squares of these two different terms. When I do that, you'll notice, though, that both of the terms I'm squaring on the inside will then have an I naught squared factor, which I can factor out. So let me factor that out. I naught times the square root of r squared from this side, and then I have my second term plus 1 over omega c, which somehow is acting somewhat like a resistance, minus L times omega, which also has units of resistance, and this is then squared. And then finally, I can find the phi that will make this equation work as well. The phase phi, we can see, can be determined using, again, basic trigonometry. The tangent of phi would be the opposite over the adjacent, and I like that because then the I naughts cancel out. So tan phi is this factor over that factor, which means phi must be the arctangent of that ratio, and the ratio whose arctangent I need is 1 over omega c minus L omega as my numerator, because my I naughts cancel out, of course, and then r on the bottom becomes my denominator. Very good. So we have then a solution which works. This shows that we can actually engineer our solution for I naught by picking an appropriate choice of phase, which is determined by this equation. And finally, I can solve to find what I naught would have to be. The current, the amplitude of the current oscillations then must be equal to the input voltage divided by this very interesting factor of r squared plus 1 over omega c minus L omega squared. Now, before we interpret what all of this means, now that we know what the current response is and the phase relation between the input voltage and the input current, there's just a little bit of terminology I would like to introduce to you, because notice that we have said there are these factors here that seem to act in some way like resistances, and there's special terminology that goes along with this that I'd just like you to be familiar with. So what this factor here, which acts somewhat like a resistance, right, because it multiplies I and has units of resistance, this is called a reactance. It's typically given the symbol X, and this is the reactance from the capacitor. This is what's known as the reactance of an inductor. And the resistor itself, you can also think of having a reactance, but in that case, its reactance really is just its resistance. So these things are all called reactants, these X terms that act a lot like resistances. And there is another term here that is also acting like a resistance, right? We typically write voltage equals I times R, or that the current in a circuit is the voltage divided by some kind of a resistance. So this factor, that is the proper composition of our reactances in order to give us the relationship between the voltage and current amplitudes, this also has a name. This is typically called the impedance of our circuit.